Hello everyone. This is a project which is about uh, the EV fleet charging management and with the V2G planning on IEEE-33 bus system optimization method, which is a built-in function of the MATLAB, is considered right over here. And I just open up the figures and tables. So I show you the problem and the uh, how much we have solved this problem. So here we have considered EV fleets. We have not considered a single EV. We consider a group of EVs. Each fleet, the number of EVs and the load is, I will show you later, and there is a proper specification for that. That's why we have different fleets, state of charge, and they have of different type of characteristics. And that, here you can see in the result summary, you can see that the target SOC for each fleet is mentioned here, and the final SOC here you can see right over here. So let me explain through the figure number 2, which is the SOC evaluation. So as I explained earlier, here we have the four fleets. Here the yellow line which represent the third fleet. Notice right over here that at the 8th hour, here on x-axis we have from 1 to 24 hours. This is a place from 1 to 7 hour. We are going to charge our fleets, and at the 8 hour you can see there is a peak. That peak actually showing us that our fleets are getting a little charged. And then at this point here you can see a dip, this dip. So at this point right over here from 1 to 7, we charge our fleets. That is a time when there is which is off peak, or in morning we just have charge our fleets. And this is the time here when you see a dip. So this is the time when we have to discharge our fleets, and we have to supply our power into grid to stabilize the grid. So the next line, which is straight up, the algorithm realize that at this point right over here, this point from 23 24 hours, the cards have to leave. So each at this point, so it start from switched from selling mode to fast charging mode. So at this point they are charged, and here you can see that their SOC is around 90%, which you can see here. The target SOC we have achieved that. And next, let me explain this the impact on the grid load. So from this to this, which is our daytime, so you can see a lot of momentum or a lot of variation right in the middle of the day. So let me start with the blue bars. So these blue bars which are going up represent the charging. The bars which are going down represent V2G discharge. So in the bottom graph, which is the total system load. So the red line is actually our total system load, and here you can see that it peaks higher than our base case. The dashed line which are our normal base case, and with the EVs, when our EVs are getting charged, our load increase. That's why we have the red line with EV. And this have a little of I mean our total load, system load increase. So this is the load characteristic curve, and here is our figure 3 voltage profile, which is about the constraint part or the other part. So this is the crucial insight. From here we can take a look that the current grid, our current system is a little weak to maintain the system voltage throughout the day. So 0.9 voltage limit, which is actually we have set uh, this as the physical limits of the grid, and our grid is not capable to remain up to above 0.9 voltages. It drops below 0.85, which is not good, so we need to further maintain it. But here you can see due to the EV fleets right over here, and from 7 to 8 hours, here if you see from 7 to 8 hours, when our from 8 to 11 hours, when our fleets have to discharge. So this is the point when our voltages are maintained. We are done with the first part, and now it's time to explain the each script files, how these script files work. I just explain the plots before, so you just got an idea that what exactly we are going to achieve, and how the process were done together. So now let me open the script files. So first of all, let me open the IEEE-33 data file. So based on this branch matrix, we have to calculate the voltage drops and currents and all the process. So next one is the generate EV fleets. So in this file, we have considered the fleets. So the basic formula here is the battery size single, means battery size and the numbers of cars which are selected inside the fleets. So inside this loop, it actually calculates the total capacity of each fleet by multiplying the number of the cars by their battery size. So this allows us to treat a whole parking lot as one combined fleet. And the next file is objective cost.m. So here in this objective, we have considered a lot of parameters like electricity cost, degradation cost, which is considered for the batteries. When we have to use our batteries for a long period of time, then we have to consider this degradation cost factor. And the final function, which is the main function here in this file, is the SOC for penalty. So here is a little logic for it. So what exactly we are going to achieve here is, so the logic checks if the final SOC meets the target SOC. If our battery is not full enough, it adds a massive financial, here it is checking, and if it's true, uh, then it have to add a massive financial penalty, which actually have to prioritize the charging the driver's cars over making a quick profit. And here is the formulation for that. And next one is the system constraints. So let me open that. So here in the system constraints, the purpose of this file is to which is actually a kind of safety inspector for our voltage parameters. So this is actually the most complex file here. So in this we have run the backward forward voltage load flow method, which already explained on our YouTube videos various times. So, and here is one more important function, which let me show you that. Where is that? Here you can see. So this optimizer tells if the voltage anywhere in the city or at a specific bus drops below 0.9, the solution is invalid. So it forces the EVs to slow down charging to save the grid. And the next one, the final one, is the main EV V2G file, which is our main file, which we have to run this file. So it combines all the other files into it. Here is the fleet configuration, and first fleet is installed at the bus 5, second at the bus 15, and the others. So we just mark them as office, commercial, industrial, and school. Okay, here let me. So here is the function which is considered as the optimization method. So this solver, it considers the cost functions and the constraint functions we just looked at all the before, and then it iteratively tweaks, checks all the charging schedule from 1 to 24 hours many times, maybe hundred and thousands of time, until it finds the perfect balance between the low cost and the grid safety. So low cost in term of the penalty factors, and the grid safety in form of the voltage profiles which I show you in the start of this video. So, and then we have some plots, and here is the table. Let me run the program again. I have to just run. You can see it takes a bit time, and this is the fmincon plots. Here you can see that the plots are here, which already explained. So that's it for today, and in this video hopefully you have understand. If you have any question, you may leave in the comment section. If you want me to create a video about specific topic, just mention that topic in the comment section. Thanks for watching. Have a good day.